Today's notes are on finding the inverse of a function. An inverse relation is the set of ordered pairs obtained by switching the input and output of each ordered pair from the original function. So you're going to switch the domain and the range. Inverse functions are like inverse operations. They undo each other. You can find the inverse of a function by switching the x and y in the original equation and solving the new equation for y. Inverse functions are reflections of one another over the line y equals x, and the notation is f raised to the power of -1. The -1 is in the position like an exponent, but it does not mean the same thing. It is a notation. It does not mean that you need to move your answer to the denominator. So we're going to go down and look at a couple examples. For example 1, it wants you to find the inverse of the given function. So we're going to change all of the inputs to outputs. And all of the outputs to inputs. So I'm going to move -2, -1, 0, 1, and 2 to be the x's. So we're flipping the x and the y. You can do the same thing for graph B. I'm going to identify a few points on my parabola. So I'm going to use the points -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And to find the inverse graph, I'm going to, just like before, flip x and y. So I'll have 4, -2, 1, -1, 0, 0, 1, 1, and 4, 2. And I'm going to plot our new points. And that gives me my graph of my inverse function. We're going to look at examples C and D in class, so please flip it over to look at example 2. The backside of our notes is going to have us check whether or not two functions are inverses of each other. Remember that like inverse operations, they undo each other. So if the composition of f of g of x equals x, and the composition g of f of x equals x, then you can say that g and f are inverses. So I'm going to start by testing f of g of x. Which means I'm going to start with my f function, and I'm going to copy down everything except for the x. Instead of the x, I'm going to put parentheses. Then, inside of the parentheses, I'm going to plug in the g of x function. So that's going to be the -1/3 x plus 2. From here, I'm going to simplify the right side of my equation and see if I get x as an answer. So I'm going to distribute -3, which will give me x minus 6 plus 6, which simplifies to x. You also need to check g of f of x, which means this time I'm going to start with the g function. So I have -1/3. Instead of x, I'm putting parentheses again, plus 2. And I'm going to plug in my f function, which is -3x plus 6. I need to distribute the -1/3 to get x minus 2 plus 2, or again, simplifies to x. Because both simplify to x, I can say that these two functions are inverses of each other. They would not be inverses if one or both did not simplify to x. We will look at example B tomorrow. So look at the bottom of your page. As a review, remember the vertical line test? We used it to tell whether or not a graph was a function. It says if vertical lines touch a graph in only one area per line, then the graph is a function. This time we're using the horizontal line test. It is used to tell you if a graph's inverse is a function. It says if horizontal lines touch a graph in only one area per line, then the graph's inverse is a function. So for part A, it wants to know, is the inverse of 3x squared minus 2 a function? Which, if you have your graphing calculator, you can use to help you get a picture. This is what the sketch of that graph looks like. So I want to know if I draw a horizontal line through this graph, does it touch it more than one spot? Since it does, this is not a function. And I'm going to do that for graph B and C as well. No matter where I draw a line on graph B, it will only hit the graph in one spot, which means the inverse graph will be a function. And line C, or example C, I'm drawing a horizontal line. It crosses my graph in two spots. So the inverse of this graph will not be a function. We will look at the rest of the examples in class.